Lab 2 technical presentation by Group 5. As you can see, our thesis here is understanding Boolean reduction and increasing familiarity with the use of IC chips can lead to multiple benefits for the user and manufacturer alike. In this part 1, we're going to look at how to derive a Boolean equation from a truth table and then reducing it down. So here's our truth table. Now if we were to grab all of the truths here and convert them out to Boolean equations, this is what we'd have. And if we were to just strictly write that into a circuit, it would look something like this. But there's two ways we can reduce it, with theorems and with cardinal maps, or K-maps. First, let's look at reducing it using theorems. As you can see, we take this huge long Boolean logic equation up at the top, reduce it all the way down to a C0 or B0 and D0. Now let's look at using a K-map. First, we write out our minterms, and we draw our K-map here. Then we place the minterms into the map, making sure they follow the correct order. And then we write the results of those minterms in. Now we're going to circle them in powers of 2 here. The first one is fairly obvious. It's these 8 that are over the top. The next one's a little bit more complex, but it's using the 4 corners here. Now we're going to reduce it out and take out the parts that change. Since the top one goes all the way across, we get rid of A and B, and then we just have to worry about one of the other two. And since we see that D changes, we just keep C. And then we take the 4 corners, doing the same thing, and we get B0 and D0.
Part 4 of the lab has us design the circuit using AND, OR, and NOT gates. First we invert B, C, and D. Next we will add B0 and D0. Last we will OR C0 with B0, D0. The resulting circuit is much simpler than the original. In part 5 we design a circuit using the 7400 series of integrated circuits. First we invert B, C, and D with the 7404, not IC. Next, add B0 and D0 using a 7408 IC. Last, we will use a 7432 IC or a C0 with B0, D0. However, we have learned about universal logic gates or functionally complete gates that may result in a even cleaner and simpler circuit. In part 6, we use the non-universal logic gate with a reduced equation. Because the NAND gates are functionally complete, we can use them exclusively to replace other gates. Here we show how to replace a NOT and OR gate with a NAND gates. We can replace the gates from the first circuit with NAND gates. First the OR gate, then the AND gate, and finally the NOT gates. Don't forget to remove double inversions. Here is the resulting circuit using only NAND gates. Because we now have only NAND gates, we can significantly reduce the amount of ICs in a physical circuit. In part 7, we create such a circuit using only NAND ICs. Working from our previous NAND circuit, we first invert B and D, then NAND B0 with D0, and finally the result with C. The resulting circuit uses only a single IC.
Part 8 has us count up the ICs, gates, and input pins to compare the differences. First, let's look at the original 10-term logic equation. We would end up with 4 NOT gates, 10 AND gates, and 3 OR gates for a grand total of 17 gates. To implement that equation with physical 7400 parts would result in 8 ICs and a convoluted mass of traces similar to the image here. Using the simplified equation, we can count these gates and input pins much more quickly. Here in the AND, OR, and NOT circuit, we end up with 5 gates and 7 input pins. The 7400 version requires 3 ICs and 7 input pins. While the NAND gate circuit uses 4 gates and 8 input pins, only a single NAND IC and 8 input pins are needed for the 7400 circuit. We conclude that by reducing and simplifying Boolean logic equations, we can reduce cost, production time, required resources, energy consumption, and also increase the speed of circuits and the technology that used them.